Hey, it's Miss Heaton signing in to talk with you about collision theory. If you want to find this in your textbook, it would be chapter 17.1 to 17.2. We're going to be talking in our next few weeks about kinetics. Kinetics is basically just looking at how fast reactions go. So we call that a rate or a speed. Rate is the more chemistry appropriate word to use. What we're going to be looking at today is specifically why do reactions happen or not happen, and what can we do to speed them up, to make their rate increase. So the first thing we need to look at is what collision theory is. And it's just what it sounds like. Boom, it involves collisions. Basically what it says is that in order for a reaction to take place, the reactants have to collide. You can't get things to react if they never come in contact. Specifically though, there's two different things that the collision must include. Requirement one is that the atoms, or the molecules when they collide, have to have the right orientation. Let me give you an example of that. So if we're looking at this reaction, hydrochloric acid reacting with lithium, we need to look at the reactants because the products colliding doesn't matter. All we care about is that HCl collides with lithium at the right orientation. First of all, let's look at a wrong orientation. So here's our hydrochloric acid. We could bombard lithium at it all day long and nothing would happen because this is the wrong orientation. The lithium is hitting the hydrogen, and those don't need to react with each other. What we want to see is the lithium and the chlorine combine and the hydrogen be left alone. So this would be a wrong orientation. Therefore, no reaction would happen. On the other hand, a collision where the hydrochloric acid here is bombarded with lithium on the left would result in a reaction. Let's see that again. Hydrochloric acid has a lithium come in and they react. That is a correct orientation, so the collision is likely to result in an actual reaction. The second requirement for a collision under collision theory is that the collision must happen with the atoms colliding with enough kinetic energy. Remember, that means how fast they're going. If the atoms collide with enough energy, the reaction will occur. This amount of energy, or the minimum amount of energy that they have to have, is called the activation energy, EA. And we'll be looking at that more and more in this unit. So let me show you an example here with our lithium and hydrochloric. If they come at each other very slowly, they'll just bounce off. If, on the other hand, they are coming in at a rate that is energetic enough, boom, a reaction will occur. Let's see that one again. Boom, reaction occurs. Let's talk a little bit about this activation energy. This is kind of a preview of what you're going to see in a later screencast. But we've talked about how the reactants have a certain amount of energy and the products have a certain amount of energy. This is an exothermic reaction, but it's not just the reactants having a certain amount of energy and going directly to products. In fact, the atoms have to collide, the reactants have to collide with enough energy to get to the top of this hill, and then they can release all the energy as they fall back down to the ground state. We'll be looking at that kind of diagram more. Don't worry too much about that for now. Now, let's apply these two criteria to explain how we can make the kinetics, the rate of a reaction, increase. We're going to look at 5 different factors. And the first one, well, all of them actually have to deal with this fact of making the collisions more effective. So not only making more collisions, but also helping them collide at the correct orientation and with more energy. So the first factor we want to look at is surface area. Over here on the left, we have a big chunk of something. So this has a low surface area. Very little of it is exposed to the liquid around it to react. On the other hand, if we crush it up or grind it up, we're going to have a high surface area. Which one do you think is going to react faster, the big chunk or the ground up one? Obviously, the ground up one, or the one in smaller pieces will, because when it's ground up into smaller pieces, there's more surface area exposed to be collided with, which will result in more collisions, which means that there's a greater likelihood that some of those collisions will happen at the right orientation and with enough energy. Factor number 2, temperature. When the temperature increases, the particles are going to gain energy, they're moving faster, and so those collisions are going to happen with more energy. Meaning more collisions are going to be at the right energy, the activation energy, which means more collisions are effective. Therefore, we have a faster reaction. Third factor is concentration. So looking at these two containers, the one on the left has a lower concentration, and the one on the right has a higher concentration because there are more particles in a smaller or in the same area. What is going to react faster, the one with more particles or the one with less? Well, it's going to be the one with a greater concentration, because if you increase the concentration, those particles are going to be more likely to collide with each other because they're closer together. They're just going to run into each other more often. Fourth factor, nature of the reactants. There are just some things that are never, ever going to react with each other. Helium and neon both have full valence shells, full octets. There's never really a way you're going to get them to react, no matter how often they collide. On the other hand, there are some things that react very quickly. For example, an ion like silver colliding with an ion like chlorine almost always will result in a reaction. They're attracted to each other because they have opposite charges, and they don't have to break any bonds. So it's going to be pretty easy for the Ag plus and the Cl minus to get together and react. And then there's some things that are a little bit slower, but actually will react if you give them enough collisions and enough time. An example of this would be carbon monoxide and oxygen. They will collide, enough to eventually cause the bonds to be broken and the new bonds to reform and make CO2. The more complex your reactants are, the slower they tend to react. Not always, but that's kind of a general idea. And again, it just has to do with how many bonds have to be broken, how many things have to collide at the same time with the right orientation. And our fifth factor is a catalyst. You've heard about catalysts before in biology. You may have heard them referred to as enzymes. That's a biological catalyst. A catalyst is just something that speeds up the reaction without being consumed or used up. So if you start with 10 of them, you'll end with 10 of them. What this does is it actually lowers the activation energy so that more reactions are able to be effective. So maybe if you used to have 10 kilojoules to make the reaction effective, now with the catalyst, it provides a pathway where that can happen with less energy. So a greater percentage of them will meet that minimum energy requirement. With that graph we were talking about, with the reactants going over the hill to get to the products, the activation energy was, the distance they had to climb to get up the hill. A catalyst makes that amount of energy a little bit lower, so it makes the hill easier. And here's kind of a simplified image of how that works. Maybe this green thing is your catalyst, and it's trying to get the pink and the orange atoms together. What it does is it provides a site where that orange and pink can kind of sit, be in the right orientation near each other, and collide, allowing them to react more often. Whereas maybe if they were by themselves, the orange and the pink would have a hard time getting into the right orientation in order to react. Folks, that's all there is to collision theory. Remember, what we were doing was explaining why reactions do or don't happen. They have to collide with enough energy at the right orientation. And we talked about the 5 factors that affect reaction rate. And we use collision theory to be able to explain how each of those factors makes more effective collisions. And that's all, folks. Ms. Heaton signing out.